Welcome back to the Deep Dive. Today, we are really getting into the weeds on something absolutely fundamental, maybe the most critical service in AWS, but also one that gets tripped up a lot: identity and access management, IAM.
It really is the bedrock, isn't it? You have to think of IAM less like just another service and more like the security control plane for your entire cloud setup. It's doing two main jobs:
Hmm.
authentication, proving who you are, and then authorization, figuring out what you're actually allowed to do.
And if you mess that up,
Yeah, if you get IAM wrong, honestly, all your other security efforts, your fancy network rules, your encryption, they can often just be bypassed completely. It's that fundamental.
okay, so the stakes are definitely high. The sources we pulled for this deep dive, they all hammer this point home. IAM is foundational. So our mission today, yours and mine, is to get past the sort of dry AWS docs, the endless JSON examples.
Right.
We need to pull out the stuff you can actually use. Actionable insights about how IAM is built, what the really effective security controls look like, and crucially, look at where things went wrong, how preventable mistakes, misconfigurations, led to some really big public incidents.
Yeah, and it's not theoretical. This is the difference between running smoothly and, well, ending up as a cautionary tale.
Exactly. And let's just put a number on that right away because this really jumped out from the research.
The 80% one.
Yeah, that one. Analysis suggests that just by properly implementing least privilege, giving only the permissions needed, and doing regular access reviews, organizations could probably stop something like 80% of the common IAM-related security problems.
80%. It's huge. And it tells you something really important. Most cloud breaches aren't AWS failing. They're customer configuration errors.
We're shooting ourselves in the foot, basically.
In many cases, yeah. The risk is largely within our control to manage, and that's why IAM is so vital strategically. It's the gatekeeper. It plugs into, what, over 200 AWS services now?
Something like that, yeah.
You literally can't do anything. Launch a server, query a database, drop a file in S3 without IAM checking that request first. It's the absolute central pillar for your security.
Okay, let's start peeling back the layers of this architecture. You said it's a decentralized, policy-driven model.
Yeah.
But before we even get to users and roles, there's this complexity that trips people up, especially with automation: eventual consistency.
Ah, yes, eventual consistency. It sounds simple, but it bites. It just means when you make a change in IAM, like you add a permission to a role or remove one, that change doesn't happen everywhere instantly across the globe.
Because AWS has to copy it around.
Exactly. They replicate IAM data across all their regions for resilience. So it might take a few seconds, maybe even, up to a minute or two sometimes, for your change to be fully reflected everywhere.
Okay, so why is that a practical problem? If I'm building something, why do I care if it takes 5 seconds?
Well, think about automation scripts. Let's say your script removes a dangerous permission from a role. And then the very next command in your script tries to delete a resource that just moments ago that role could delete.
Ah, I see. The script might be faster than the replication.
Precisely. If the delete command runs before the permission removal has fully propagated, the delete might actually succeed based on the old, now revoked permissions. You thought you closed the door, but for a brief moment, it was still open.
So you need to build in pauses or checks.
You absolutely have to account for it in fast-running automation that depends on IAM changes taking effect immediately. Add delays, maybe check the state before proceeding. It's a crucial operational detail.
Good tip. Okay, now let's get into the building blocks, the who in IAM. Right at the very top, we have the root user.
The root user. This is the original identity created when you first signed up for the AWS account.
Yeah.
It's God mode. Absolute, unrestricted access to everything, billing, closing the account, everything.
So you really shouldn't be using it day to day.
Absolutely not. The guidance is crystal clear. Treat the root user like a physical key in a safe. You only bring it out in emergencies like break glass scenarios.
Odd kind of emergencies.
Things only root can do. Maybe recovering a compromised account, changing critical account settings, or actually closing the account down.
Yeah.
And you must have MFA on it, ideally a hardware token, and keep those credentials locked away securely offline.
Because if root gets compromised,
You've lost the kingdom. Game over for that account, potentially your whole AWS organization if it's the management account.
okay, moving down from root, we have IAM users. These feel more familiar.
They are more familiar, yeah. These typically represent actual people or sometimes applications that need long-term access. The key thing is they use long-term credentials, static access keys and secret keys for API access, or a password for logging into the AWS console.
And the sources seem pretty down on these.
Overwhelmingly, yes. Because those static credentials, they never expire unless you manually rotate them. If someone accidentally commits an access key to GitHub or leaves it in a configuration file on a server,
An attacker potentially has access forever or until it's discovered?
exactly, it's a huge risk vector, which is why the strong preference, almost a mandate now, is for the next component, IAM roles.
Roles. These are different because they're temporary.
Right. Roles are the cornerstone of modern zero-trust thinking in AWS. They are temporary, assumable identities. They don't have their own long-term credentials like users do.
So how do they work? How does something use a role?
When a service, like an EC2 instance or even a federated user, needs to act as that role, it makes a call to the AWS Security Token Service, STS. STS checks if the request is allowed, and if so, it issues temporary security credential.
How temporary?
Usually pretty short-lived, could be an hour, could be configurable up to 12 hours max. But the point is, they expire.
And that drastically shrinks the window if those temporary credentials leak out.
Massively reduces the blast radius, yes. If someone steals a temporary token, it's probably useless within an hour or less. Roles are perfect for giving permissions to AWS services, for cross-account access, for users logging in via federation. They avoid hard-coding secrets everywhere.
Makes sense. We should also quickly mention IAM groups.
Groups are straightforward. They're basically just containers for IAM users. You attach permissions to a group, say a developers group, and then any user you put in that group automatically inherits those permissions.
So it's for role-based access control, RBAC.
Exactly. It's the foundation for RBAC for your IAM users. Simplifies managing permissions for lots of users. But, and this is key, groups are only for users. You can't put a role in a group, and groups don't deal with temporary credentials. They're purely a user management construct.
Okay, so we've covered the who root, users, roles, groups. Now let's talk about what the permissions themselves, defined in policies, these JSON documents. Two main types.
Yep. First, you have identity-based policies. These get attached directly to a principal, so attached to a user, a group, or role. They define what that specific identity is allowed to do.
And the second type.
Resource-based policies. These are attached directly to the resource itself. Think an S3 bucket policy, or a policy on an SQS queue, or a KMS encryption key. These define which principals, potentially even from other accounts, are allowed to access this specific resource.
And inside these policy documents, there's some key elements that control everything. There's the effect.
Which is either allow or deny. Simple enough.
Then the action.
That's the specific AWS API call being permitted or denied, like s3.getObject, ec2.start instances, dynamod beat.pewItem. You need to be specific here for least privilege.
Then the resource.
Which specific thing the action applies to, identified by its Amazon resource name, the ARN. Could be a specific S3 bucket, a specific EC2 instance, or you can use wildcards.
And finally, the condition. This sounds powerful.
Oh, it's incredibly powerful. Conditions are what let you add context and logic. A policy isn't just user A can read bucket B. It can be user A can read bucket B only if they are coming from our corporate IP range, or, maybe more importantly, only if their authentication included multi-factor authentication.
Using context keys like Oz source heap or AGOT multi-factor Oz prison?
Exactly. Conditions turn static permissions into dynamic, context-aware rules. They are absolutely essential for fine-grained security.
Okay, this is probably the most critical part to understand, the evaluation logic. We can have permissions defined all over the place on the user, maybe on the role they assume, on the S3 bucket they're trying to read. How does AWS figure out if the final answer is yes or no?
This is the heart of IAM security design, and it's built to be safe by default. The first rule is implicit deny. If nothing explicitly says you can do something, then you cannot do it, period.
Default deny.
Makes sense. But what happens when you have multiple policies that might apply, and maybe they conflict? Like my user policy says allow S3 read, but the bucket policy doesn't mention me, or maybe it even says deny.
What takes precedence?
There's a whole sequence, about 7 steps AWS evaluates, but the single most important rule, the one that overrides everything else, is the power of explicit deny. If any policy that applies to the request, whether it's an identity policy, a resource policy, or even an organizational policy we'll talk about later, like an SCP contains an explicit deny statement for that action.
That's right there.
Instantly, game over. That explicit deny trumps any allow statement anywhere else. Doesn't matter if 10 other policies say allow, one deny wins.
So let's say I'm a developer. I write a role policy that accidentally gives way too much S3 access. Allow. But the central security team has an organizational policy, an SCP, that explicitly denies access to certain critical buckets. My mistake doesn't matter.
Your overly permissive allow is completely overridden by that central deny. The request fails. This is the failsafe. It's designed so that central security controls can prevent local configuration errors from causing breaches. Understanding that explicit deny is king is absolutely fundamental to designing secure IAM setups.
All right, so we know how policies work. Now, applying them. The absolute golden rule, the mantra everyone repeats, has to be the principle of least privilege.
Grant only the permissions absolutely necessary to perform the task and no more. It sounds obvious, right?
It does, but that statistic you mentioned earlier suggests we're really bad at it in practice.
We are astonishingly bad at it. That Datadog finding 70% of existing IAM policies being overly permissive is just shocking. It means we're constantly giving out keys to the entire building when someone just needed access to one room.
Giving S3, when all they needed was S3.object for one specific bucket.
Exactly that kind of thing. Or maybe an EC2 instance role has permission to talk to DynamoDB, but looking at the logs, it hasn't actually made a DynamoDB call in 6 months. That unused permission is just sitting there waiting to be exploited if the instance gets compromised. This permission sprawl is the attacker's best friend for moving laterally.
And this directly connects to why there's such a big push for the principle of temporary credentials, right? Using roles instead of users.
Absolutely. They go hand in hand. The whole strategy is to minimize, or ideally eliminate, the use of those long-lived static access keys that IAM users have. If you rely on IAM roles and the temporary tokens from STS instead,
Which expire quickly.
right, often in an hour, then even if an attacker manages to steal a credential, their window of opportunity is tiny. It contains the potential damage automatically. It's a huge security uplift compared to static keys floating around.
This seems especially relevant for managing workforce access and federation. Trying to create individual IAM users for everyone in a company sounds like a nightmare.
It's completely unscalable and incredibly risky. Imagine onboarding, offboarding, role changes, managing hundreds or thousands of IAM user accounts manually. Forget it.
So federation is the way.
Federation is the only sane way for workforce access at scale. You use something like IAM Identity Center, which used to be called AWS SSO, or you integrate directly with your company's existing identity provider, your IDP. That could be Okta, Azure AD, Ping Identity, whatever you use.
And you connect them using protocols like SAML or OADC.
Correct. And the real beauty here is the separation of concerns. You decouple identity management from permission management.
Explain what that means practically.
Okay, so your corporate IDP Okta, say, handles the user lifecycle. It knows who the employees are, their job titles, their departments. It's the source of truth for identity. When an employee leaves, HR disables their Okta account instantly.
And AWS IML.
AWS IAM then only worries about permissions. What can the developer role do? What can the auditor role do? When an employee logs in via Okta, Okta authenticates them and then, based on their group membership perhaps, allows them to assume a specific IAM role in AWS. They get temporary credentials for that role.
So if that employee leaves and their Okta account is disabled,
Their ability to assume any AWS role instantly disappears. No need to hunt down and delete IAM users across potentially hundreds of AWS accounts. Access is cut off at the source, cleanly and immediately. Centralized, responsive control.
makes perfect sense. Now, shifting from people to machines. Workload automation, how do our applications get permissions?
This is where roles are absolutely non-negotiable best practice. Your EC2 instances, your Lambda functions, your containers running in ECS or EKS, they should always use IAM roles to get permissions.
Never hard-coding access keys in the code or config files.
Never, ever do that. If your Lambda function needs to write to a DynamoDB table, you create an IAM role with Dynamod. Put item permission, you assign that role to the Lambda function, and AWS handles delivering temporary credentials to the function automatically when it runs. Clean, secure, no static keys involved.
What about hybrid setups? Servers running in my own data center that need to talk to AWS.
That's a great use case for a service called IAM Roles Anywhere. It basically extends the role-based temporary credential model outside of AWS. You can configure it so your on-prem servers authenticate using standard X.509 certificates, which most enterprises already manage, and in return, they get temporary AWS credentials to call AWS services directly.
So no need to manage AWS access keys on those on-prem servers either.
Exactly. It brings that secure, temporary credential model to your hybrid workloads. No agents needed, just certificate-based authentication to STS.
Okay, let's tackle a big scaling challenge. ABAC versus RBAC. We touched on role-based access control RBAC with groups. You mentioned a risk of role explosion.
Yeah, RBAC is intuitive to start with, right? Create roles for job functions. Developer, tester, database admin. Assign users to roles. Simple.
But in a big company.
It breaks down. Imagine you have, say, 20 different development teams working across 10 different projects, each with dev, test, and prod environments. If you strictly follow RBAC, you might need a specific role for Team Apollo Project Phoenix dev environment.
Oh, wow. That's 20 times 10 times 3, 600 roles.
Exactly. You end up with hundreds, maybe thousands of very specific roles. Managing them, keeping their permissions accurate, auditing them, it becomes a nightmare. That's role explosion. It leads to complexity, and complexity often leads to security gaps or people just getting assigned overly broad roles because it's easier.
So attribute-based access control, ABAC, is the proposed solution. How does that work using tags?
ABEC flips the model. Instead of creating tons of specific roles, you create fewer, more general roles, but write policies that make decisions based on attributes or tags attached to both the principal, the user or role assuming the policy, and the resource they're trying to access.
Give me an example.
Okay, let's say you tag your IAM users or roles with a team tag, e.g. team backend, and a project tag, AG project alpha. You also tag your S3 buckets and DynamoDB tables with the same project tag.
Right.
Then you write a single policy that says something like, allow S3.object on any S3 bucket if the principal's project tag exactly matches the bucket's project tag.
So you're using condition keys in the policy.
Precisely. You use conditions like Oz.principalTagProject and OzResourceTagProject to compare the tags. The policy itself is quite simple and reusable. When a new project starts, you don't need a new policy or role. You just make sure the new users and resources are tagged correctly with the new project name.
That sounds much more scalable long-term. But what's the catch? It sounds like you need really disciplined tagging.
That's the main hurdle, absolutely. ABA lives or dies by your tagging strategy and enforcement. If one team tags resources with project and another uses project name, the ABAC policy won't work consistently. You need strict governance around tag keys and values.
So it's more upfront work on governance for less policy management later.
Exactly. It shifts the effort. But for large, complex environments, that shift is often worthwhile. What most sources recommend, and what seems practical, is often a hybrid approach.
How does that work?
You use RBAC for broad, common permissions based on job function, like maybe everyone in engineering gets read-only access to certain shared documentation repositories. Then you use ABAC for the fine-grained access control to specific project resources based on tags like project, team, environment, or data sensitivity. Best of both worlds.
Okay, we've talked about writing good policies, using roles, maybe using ABAC. But humans make mistakes. So now let's talk about the controls designed to prevent those mistakes from causing harm in the first place. The guardrails.
Right, these are proactive controls. And it's helpful, as some sources point out, to think about how these map to broader risk frameworks, like NIST's privacy framework, for example.
How so?
Well, things like service control policies, SCPs, which we'll get to, they are fundamentally about governance setting top-down rules. That aligns with NIST's Govern P function. Tools like IAM Access Analyzer, which find potential problems, help with the Identify P function, identifying risks. It just frames their purpose.
Got it. So let's look at these controls that act like filters, often based on that deny logic we discussed. Starting within a single AWS account, we have permissions boundaries.
Permissions boundaries are really interesting. It's essentially an IAM policy, a standard managed policy, that you attach to an IAM user, or more commonly, an IAM role. But its purpose is unique.
How so? It grants permissions.
No, and this is the key thing people misunderstand. A permissions boundary does not grant any permissions itself. Instead, it defines the maximum possible permissions that the user or role it's attached to can ever have, regardless of what other policies are attached. It sets a ceiling.
Okay, walk me through an example. Let's say I create a new IAM role for an application. I attach an identity policy to it that says allow EC2 and allow S3, pretty broad. But then I also attach a permissions boundary policy to that same role. And this boundary policy only contains allow EC2.start instances, EC2.stop instances, and S3.getObject. What can that role actually do?
It can only do those three specific actions: start, stop EC2 instances and get object from S3. Even though its identity policy theoretically allows all EC2 and S3 actions, the boundary restricts it.
So the effective permissions are the intersection, what's allowed by both the identity policy and the boundary.
Exactly. The boundary acts like a filter. If an action isn't allowed by the boundary, it doesn't matter if the identity policy allows it, it's blocked. It only limits permissions, it never grants them.
I can see the use case immediately.
Safe delegation.
That's the primary use case.
Yeah.
Imagine you want to let a development team create their own IAM roles for their applications, which is good practice. But you're worried they might accidentally create a role that gives access to, say, your central billing data or security logs.
Right. You want to prevent that. So you give the developers permission to create roles, but you attach a permissions boundary to their IAM user or role. That boundary specifies the maximum permissions that any role they create can ever have. They can create a role, attach policies to it, but that new role is itself constrained by the boundary you set for the developers.
So they literally cannot create a role that's more powerful than the boundary allows.
Correct. It prevents privilege escalation through delegation. Very powerful control within an account.
Okay, now let's zoom out. The ultimate guardrail, operating across potentially hundreds of accounts in an AWS organization. Service control policies?
SCPs.
SCPs are the heavy artillery for central cloud security and governance teams. They are policies, but you don't attach them to users or roles. You attach them to organizational units, OUS, or even the entire organization root within AWS organizations.
And they affect all the accounts under that OU.
Yes, and their impact is profound because of how they interact with the evaluation logic we discussed earlier. Remember the explicit deny rule?
That an explicit deny always wins. Well, an explicit deny in an SCP applied to an account cannot be overridden by anything within that account. Not by an IAM identity policy, not by a resource policy, not even by a permissions boundary. The SCP deny is absolute within that account.
Wow. So if the central security team puts an SCP on the developer's OU that says, deny IAM delete role for critical administrative roles,
Then no one in any account within that developer's OU, not even the local account administrator, can delete those specific roles, period. The SCP acts as a top-down, non-negotiable guardrail.
what are common uses for SCPs then?
Lots of governance use cases. Denying access to specific high-risk AWS services that the company hasn't approved. Forcing data residency by denying actions outside of approved AWS regions. Usually you block everything except us East 1 and us West 2. Enforcing security configurations like maybe denying the creation of S3 buckets that don't have encryption enabled. Or ensuring certain critical logging cannot be disabled. They are essential for enterprise-wide compliance and risk mitigation.
So boundaries are for delegated admin within an account. SCPs are for organization-wide guardrails. Both rely on that deny logic. Now, what about finding problems after things are deployed? We need continuous monitoring tools.
Yeah, absolutely. And top of the list here is IAM Access Analyzer. This service is fantastic. It uses some pretty advanced techniques called automated reasoning or formal methods.
Like mathematical logic.
Sort of, yeah. It analyzes your resource policies, the ones attached to S3 buckets, SQS queues, KMS keys, Lambda functions, etc., and it mathematically proves whether those policies grant access to any principal outside of your defined zone of trust, usually your AWS organization or account.
So it finds things like S3 buckets accidentally made public.
Yeah.
Or cross-account access you didn't intend.
Exactly. It proactively flags potential external or public access based on policy analysis before it leads to a data leak. It gives you findings like, hey, this S3 bucket policy allows access from account 12345678901, which is outside your org, invaluable for preventing accidental exposure.
That sounds vital. Now, going back to that 70% statistic policies that are too broad but already deployed, how do we safely shrink them down?
That's where another feature of Access Analyzer comes in, sometimes called activity-based policy generation, or generating least privilege policies. It ties into AWS CloudTrail.
CloudTrail logs all the API calls, right?
Right. Access Analyzer can look at the CloudTrail history for a specific IAM role, say, over the last 90 days, and see exactly which AWS services and actions that role actually used.
And then?
It can automatically generate a new, fine-grained IAM policy that includes only those permissions that were actually used. It takes you from a broad, potentially risky policies down to exactly what the application needed. Describe instances, EC2, run instances with specific parameters, etc.
So it helps you achieve true least privilege based on observed behavior.
Precisely. It provides a data-driven way to systematically identify and remove excessive permissions from your roles, significantly reducing the potential attack surface if that role's credentials ever get compromised.
Okay, theory and tools are one thing. Let's connect this to the real world, the painful lessons learned from actual incidents. The sources pointed out a scary trend. IAM abuse tactics jumped something like 134% in 2025. Attackers know this is often the weak link.
They absolutely do. And these case studies aren't just about blaming companies, they're crucial learning opportunities. They show how often a relatively contained initial compromise blows up only because it hits an overly permissive IAM configuration.
Let's start with the big one, often cited. Capital One in 2019, huge breach, 100 million records. What was the technical chain of failure there, specifically involving IAM?
The initial entry point wasn't directly IAM. It was an application vulnerability, a server-side request forgery, or SSRF, in a web application firewall, WAF, that was misconfigured.
So the attacker tricked the WEF into making requests on their behalf to internal systems.
Exactly. And the target they hit internally was the EC2 Instance Metadata Service, IMDS. This service provides information to the EC2 instance, including temporary credentials for the IAM role attached to the instance.
And the WAF instance was running this older version, IMDS v1.
Correct. IMDS v1 was susceptible to this kind of SSRF attack. The attacker was able to basically ask the metadata service, hey, give me the credentials for the role attached to this instance, and it obliged.
Okay, so they got temporary credentials. That sounds like what we want people to use. What was the IAM failure?
The failure was that the IAM role attached to that WAF instance was massively overprivileged. It didn't just have the minimal permissions needed to do its WAF job. It had broad read access, S3 list buckets, S3 get object, to dozens and dozens of S3 buckets containing sensitive customer data.
So the attacker used the stolen temporary credentials, which should have been low risk, but because the role was too powerful.
They could suddenly access and exfiltrate huge amounts of data. The lessons are clear. First, enforce IMDS v2, which uses session tokens and protects against basic SSRF credential theft. And second, and arguably more importantly, if that WAF role had followed the principle of least privilege, the breach would have been dramatically smaller, perhaps insignificant. The SSRF might have happened, but the attacker wouldn't have been able to get anywhere interesting with the stolen credentials.
A powerful lesson in least privilege. Okay, next case. CodeSpace is back in 2014. This one sounds like a nightmare scenario.
It's the stuff of cloud security nightmares, yeah.
Yeah?
It effectively put them out of business. The root cause here was simpler but just as devastating. An attacker compromised an IAM user account, likely through phishing or similar means.
A user with long-term static credentials.
Yes. And this user apparently had very broad permissions, including console access. Critically, MFA was not enabled on this user account. Yeah. The attacker logged into the AWS console as this user and essentially went on a destruction spree, deleting servers, deleting databases, deleting backups. They systematically wiped the company's infrastructure.
And because backups were gone too.
They couldn't recover. They had to shut down the business. It's a brutal example.
The primary lesson seems blindingly obvious then.
Enforce MFA everywhere. En route, on all admins, on any user that has console access or significant permissions. It's not optional. And, secondarily, monitor CloudTrail for highly unusual activity. A sudden storm of delete API calls should trigger immediate alerts and investigation.
Makes sense. Okay, a more recent one. LastPass in 2022.
Yeah.
This involved a developer environment compromise, right?
Yes, this highlights a different vector. The initial breach happened when an attacker compromised a software engineer's corporate laptop. From there, they were able to access credentials stored on that machine.
And those included AWS credentials.
Apparently, yes. IAM user credentials that provided access to LastPass's cloud-based development environments. While LastPass had customer vault data encrypted, the attacker's foothold in the cloud environment eventually allowed them to access backups of vault data and copies of decryption keys that were also stored, albeit separately, in the cloud environment.
So how could the IAM controls we discussed have helped here, even if the developer machine was compromised?
This points directly to the need for zero trust principles, even for internal developers, and specifically the use of permissions boundaries. If that compromised developer's IAM user, or better yet, the role they assumed, had a strict permissions boundary applied.
Limiting the maximum permissions they could ever have or grant?
Exactly. The boundary could have prevented that compromised identity from accessing the highly sensitive S3 buckets containing backups or the KMS infrastructure managing keys, even if the attacker fully controlled the developer's initial access. It creates segmentation. The breach might still happen on the dev environment, but the boundary prevents it from easily spreading to the crown jewels.
It contains the blast radius again. Now let's get into something more subtle. The danger of chaining permissions. Sometimes permissions that look harmless on their own become really dangerous when combined or have hidden side effects. You mentioned IAM create policy version.
Right. This is a classic privilege escalation technique that catches people off guard. You might look at IAM create policy version and think, okay, they can create new versions of an existing policy, but they can't attach it or delete it, so what's the harm?
Sounds reasonable, but wrong.
Completely wrong, potentially. The danger lies in how they create that new version. An attacker with only this permission on a specific policy might be able to craft a new version of that policy document that includes effect, allow, action, resource, full admin privileges.
Okay, but they still need to make that the active version, right? Don't they need IAM set default policy version?
This is the insidious part. Often, the API call or CLI command for create policy version includes an option, like set as default, if not explicitly restricted otherwise, for example by a condition, having IAM. Create policy version might implicitly allow you to set the new version as the default at the time of creation.
Wow. So one permission effectively becomes admin access.
In that specific scenario, yes, it bypasses the need for the separate set default policy version permission check. It's a huge escalation risk from what looks like a minor permission. Security teams need to be extremely careful about who gets IAM, create policy version and on which policies, and potentially use conditions to block the set as default option.
That's a nasty one. Okay, another chain. Combining IAM.passRole with EC2 run instances.
This is a more classic lateral movement pattern. Imagine an attacker compromises an IAM user that has fairly limited permissions. They can launch new EC2 instances, EC2 run instances, and they have permission to pass a specific, highly privileged IAM role to an EC2 instance, IAM pass role on that specific role's ARN. They can't assume the privilege role themselves directly.
But they can give it to an EC2 instance they control.
Exactly.
Yeah.
So what do? They use their EC2, run instance's permission to launch a new EC2 instance. During the launch process, they use their IAM pass role permission to attach that powerful, privileged role to this new instance they just created.
Okay, the instance is running with the powerful role.
Now, the attacker connects to the instance they just launched, maybe via SSH or SSM. Once inside, they query the instance metadata service, IMDS, hopefully V2. Because the instance is running with the privileged role, the metadata service gives the attacker the temporary credentials for that privileged role.
And now the attacker has the credentials for the powerful role.
Bingo. They've used two seemingly limited permissions, run instances, pass role, to effectively escalate their privileges and obtain the power of the role they couldn't access directly. It highlights why auditing combinations of permissions, especially IAM pass role, together with service creation permissions like EC2, run instances, Lambda, create function, etc., is so critical. So we've seen how IAM policies work and how they can be misused. But for true defense in depth, especially around data, you have to realize IAM identity policies are often just one layer of the check. Services like S3 and KMS add their own critical layers.
Yeah, you mentioned resource policies earlier. Let's start with S3 and the least privilege union. How does access actually get evaluated for an S3 bucket?
S3 is obviously critical. It holds the data, so AWS implements a layered check. For a principal, like an IAM role, to successfully access an object in an S3 bucket, permission must be granted by both the principal's IAM identity policy and the S3 bucket policy, the resource policy attached to the bucket.
Both have to say allow, or at least neither can say deny.
Basically, yes. Think of it like needing two keys to open a door. The IAM policy attached to your role needs to grant the necessary action, for example, S3.getObject. And the bucket policy attached to the target bucket must also allow that action for your principal or allow it publicly, which is usually bad.
So if my role has S3 get object permission for bucket A, but bucket A's bucket policy doesn't list my role's ARN and isn't public, my request fails.
Correct. Access denied. Conversely, if the bucket policy does allow my role, but my role's identity policy doesn't grant S3 get object, I'm also denied.
And the explicit deny rule still applies across both.
Absolutely. An explicit deny in either the identity policy or the bucket policy will block access immediately, regardless of any allow statements in the other policy. It's true defense in depth. A mistake in one policy layer can potentially be caught by the other. This, combined with S3 block public access settings at the account level, provides a robust barrier against accidental data exposure.
Okay, that makes sense for S3.
Yeah.
Now, for encryption keys with KMS, you mentioned an even stricter two-layer key policy model.
Yes, KMS is arguably even more sensitive because it guards the keys that protect your data at rest. So it has a unique and mandatory control, the key policy. Every single customer-managed key, CMK, and KMS must have a key policy attached. This policy is the primary master access control list for that specific key.
And it's separate from IAM policies.
It is. Think of it as the ultimate gatekeeper for the key itself. Now, the most crucial part of the key policy is how it interacts with IAM.
How does it work?
The key policy uses a sort of permission to delegate permission model. For IAM policies to have any effect on controlling access to a KMS key, the key policy must first explicitly grant the AWS account, or specific IAM roles users within it, the permission to use IAM policies to manage access for that key.
Wait, so the key policy has to allow the account to use IAM policies for that key before any IAM policy can actually grant access to the key.
Precisely. It's a deliberate separation. It prevents someone from accidentally granting broad access to cryptographic operations, like Calamaris decrypt, via a sweeping account-wide IAM policy like allow action Calamaris resource. If the key policy itself doesn't authorize IAM-based control for decryption for that account or role, then even allow Calamaris in an IAM policy is useless for decrypting with that specific key.
So if I'm a developer and my IAM role needs to decrypt data using a specific KMS key, what two things need to be true?
Two explicit allows are needed. One, the key policy for that specific key must grant your role or a group poster it belongs to, or the whole account if configured that way, permission for the Calamaris to decrypt action.
Yep.
Two, your role's IAM identity policy must also grant permission for the Calamaris decrypt action on that specific key's ARN.
Both checks have to pass.
Both have to pass. If the key policy is locked down tight, it doesn't matter how permissive your IAM role becomes, you still can't use the key for decryption. This ensures that control over highly sensitive cryptographic operations remains tightly bound to the key itself, providing a strong, centralized control point against IAM misconfigurations elsewhere. #outro.
Wow. Okay. We've gone from the basics of users and roles through policy evaluation, guardrails like SCPs and boundaries, horrifying incident examples, all the way to the nuances of S3 and KMS. Let's try and boil this down. What are the absolute must-do takeaways for you listening?
Number one, operationally. Get serious about moving off static IAM user keys. Embrace IAM roles and temporary credentials via STS for everything you possibly can. Workloads, federated users, everything.
Right. Minimize those permanent keys.
Number two, MFA. Multi-factor authentication. It's not optional. Enforce it on root, enforce it on admins, enforce it on any human user accessing sensitive environments or APIs. Use hardware tokens where possible. The code spaces incident is your nightmare fuel here.
And number three, don't just rely on people writing perfect policies.
Exactly. Use the proactive guardrails. Service control policies, SCPs, are essential for setting organization-wide security boundaries that cannot be overridden locally. Use permissions boundaries to safely delegate administration within accounts without risking privilege escalation. These aren't suggestions. They should be standard practice.
Yeah, keep watching.
Continuous monitoring is key. Use IAM Access Analyzer regularly to find those unintended public or cross-account access paths before they're exploited. And leverage its integration with CloudTrail to analyze actual usage and generate true least privilege policies, that 70% over-permission rate. You need a process to actively shrink it.
It really comes back to that shared responsibility model again, doesn't it? AWS provides incredibly powerful granular tools like IAM, but securing your cloud depends entirely on you, the customer, configuring and using those tools correctly.
Absolutely. Misconfigurations, like we saw with Capital One's overly permissive role, aren't flaws in the AWS platform itself. They are failures in how the customer implemented the controls provided. Your configuration discipline is your security posture.
So looking ahead, what's the final thought you want to leave people with? Where is IAM heading?
Well, the identity landscape is definitely getting more complex, not less. We're seeing this explosion of non-employee identities needing access, think B2B partners, external applications, IoT devices. Some predict these external identities will soon vastly outnumber internal employee identities accessing cloud resources.
So IAM needs to scale beyond the traditional workforce model.
It does. And alongside that, there's the huge push towards passwordless authentication, things like FIDO2 security keys, pass keys stored on devices. These aim to eliminate the risk of phished or stolen passwords and static keys altogether. So the future of IAM, I think, is about balancing this incredibly granular, policy-based control we've discussed today with the need to manage diverse identity types and integrate these more dynamic passwordless, perhaps risk-based authentication methods. How do you maintain least privilege when identity signals are changing? That's the next big challenge.
Identity is definitely the new perimeter, and managing its complexity securely is paramount. Fascinating stuff. Thank you for joining us for this deep dive into the critical world of AWS IAM.